See the dot? Okay. So the architecture design. So this is what we had before. So it kind of looks like one monolithic app, but you do have a few apps in there. But the main thing is all sharing this central database that it's probably look quite familiar. The typical problem with a lot of companies, you end up having, so these are the events or queries. Initially, you insert the data into the database. And then later on, you have, because transactions in our case are mutable. So you could have a transaction gets created, and later on it gets changed. Let's say altering the amount gets approved, and eventually you say it's paid, or invoiced or paid. So all of these were written into this central database, and at the same time, it's also consumed by this reporting service from the same place. Obviously, this application was built many years ago, and we use MySQL for the data source, or the data storage. And one of the problems also involved in here was it happens to be using the MyISM engines, as you can see, because that uses table-level locking. So to serve the report, you ended up with all sorts of problems, like replication lags, people doing aggregations, locking right. So lots of latency problems in here. So what we actually wanted, this is back to more than a year ago, was we needed the report to be near real-time latency. It doesn't have to be like ready in a second, but it has to be relatively quick. We don't, because the replication lags would be really bad, taking sometimes minutes or even hours to catch up. Really that was the situation. We wanted the user not to wait in the interface. When they press a button, it doesn't matter was it aggregations, is pinpoint queries, or they want to see something, it pretty much has to be instant to have the best user experience. The accessible of individual transaction record is one of the very interesting things, but made the problem even worse, because the report does not only contain the data that is aggregated numbers. It's much easier, right? You can do a lot of things with aggregated numbers, but at the same time, the user also wants to see all the transactions actually correlated with these numbers in a paginated way. So as you can see, there's not just aggregated data we're talking about here, but also individual records to be presented at exactly the same time with the relevant records. So, and flexibility, this is one of the most important things for us. So we don't want to build something and then later on say we want to add a new data metric. And I say, how long is going to take? 2 months, 3 months? We don't have the time for that. So we wanted something that to be really flexible, that if we need any more data metric to be added in this data store, for the report to be made available for the users, we want it to be easy in terms of the development cost, which should be minimum. And finally, it had to scale. So this is everything that we built. So it's not only means it has to scale to at present, it means for all of the, another thing Harry mentioned is we're part of the Xerox group. And the group level traffic, we're talking about 10 times more. So in order to scale for that kind of traffic, we have to really have something that is easy for us to scale in terms of, I wouldn't say zero effort, but minimum effort. Now it comes down to the solution. So the solution has, its first thing is broken things down. So rather than having all this monolithic database that everything consumes, so we've broken down the problem. The first one is producing part. So instead of only sending the data into this central database with these events, we also send these events to Kafka. I'll explain why we have to do double write a little bit later on. But at this stage, we are not only sending in the data into the central database for obvious reasons such as backwards compatibility, but also we send the data to Kafka. This little thing here is because Kafka, although it's really, really good for consuming messages and maintaining message order within the same partition, but what you probably wouldn't want to do is to keep your data there forever. And so we typically keep the data in Kafka for 7 days. So this job runs every hour to back up all of your data into HDFS, which is the Hadoop distributed file system, which really gives you the flexibility if you want to do a MapReduce job with all of that data, put it to somewhere else, rebuild your entire data source from day one. You have all of the options for that. So this is the producing part. So moving on to the next part, which is the consuming. So now we have our data in Kafka. So this central DB is already out of the picture. So So what we do here is we use Apache Spark Streaming here in near real-time manner, because Apache Spark Streaming is an addition to the original Apache Spark framework that does real-time processing. What it does is it has I will focus more on the Elasticsearch topic, but it would be useful to mention some of the details here to just give you a bit more understanding of what's going on. So this Apache Streaming has like mini batches. So instead of consuming the messages as soon as they come in, it combines the things into batches like 1,000 a batch and produce that into Elasticsearch. So within Elasticsearch, we have all of the transaction data. Obviously, you can see what's happening here because these are storing individual transactions, because Elasticsearch is really, really good from our experience to do real-time, almost instant aggregations. I'll walk into some of the more details, the technical details of why it's fast and what you can do to make it fast, but actually also save some of the cost of your cluster. So now the user can happily do sorting, grouping, and filtering with the Elasticsearch cluster instead of using the monolithic database that's used by everything else. Sorry about the language. So you always have to prepare for the worst when doing something like transaction data migration from old system to the old system. So this is probably why we keep writing into this old one as well. So at early stages, we didn't have a lot of experience working with Kafka. So to minimize the amount of risk we had, we have to think about really, okay, if something happens, what are we going to do? We don't want to just cry against, it's a nice office, but you still don't want to cry against this window just because you don't have a solution. So this really gives us the flexibility. Actually, we had this saved our lives many, many times within the transition period. If anything goes wrong, because initially we didn't trust the Kafka not losing messages because we just didn't have enough knowledge. So if anything happens that we thought, oh, why we lost some messages? To be able to still serve a report, we do a disaster recovery process. Actually, this process is fully automated. There's no human intervention in there. So it will actually exercise this twice a week just to make sure when you actually need it, it's not broken. Otherwise, the first time you use it, that is something is broken, you guarantee that you're going to have some problems. So this process is really important because it allows us to restore everything from this central DB that has the canonical data source to Elasticsearch, so the user can still use the data. There's no transaction loss. But that's not all. Double write can cause lots of problems. If you have two data sources, one is used in the report and people wouldn't trust the data. But what happens when you have two things? It's very difficult to guarantee you receive the messages in two different places unless you just retry an infinite number of times. So that's okay, but you kind of want to move away from that thing to only write into one place instead. So now we're in a good position that we do know how to use Kafka. We do know the message wouldn't get lost, what kind of guarantee it gives, what kind of acknowledgement level you set to make sure you don't lose your message. So all of that, so once we have that knowledge, we can say, okay, let's, instead of writing into this big database, which is not right scale, it probably is now, but not probably in a year, so it's to only write into Apache Kafka, and for anything that's a backwards compatibility, you go back and write into this central database. I put a few consumers here because you might not just want to have one, you might want to have a few for different kind of things. And this would really give you, at the end, to make sure your data is backwards compatible, writing into the central DB, and gives you the time to make sure you not only have the data exactly there, but also allows you to move away from the systems that are already coupled with the central DB in time. So no, you don't have to do that straight away, but once this is doing it, and then you can just start decoupling your other project applications over time. I always mention this thing. So it's something I heard from Uncle Bob Martin from quite a few years ago in the architecture talk, is a good architect always maximize the number of decisions not made. So this, why do I like this, is the thing of design some systems. if you couple with, let's say, I could, in this whole approach, we could just write the whole thing into Elasticsearch, right? Why would I even bother putting it into Kafka? Let's rewind a little bit. If we write in the data into Kafka, so let's say in this particular case, if there's anything goes wrong, let's say Elasticsearch was new to us like 1.5 years, 2 years ago as well. So if something goes wrong in there, then your whole approach is based on your canonical data source, not in Elasticsearch. It's in Kafka and in HDFS. So that would give you maximum amount of time to understand what you're actually dealing with, what you're using. If you have a problem, can you fix it? So by keeping the data in Apache Kafka and HDFS, really give us the flexibility to decouple the two. Another scenario, or product team are very talented, but at the same time they're very demanding, which is a good thing because now you get a lot of business. So when later on, what would happen is the clients would have a requirement and say, okay, can we have something that is immediate consistency? So we all know Elasticsearch is eventual consistency, but this gives you the flexibility later on if you say, okay, I want something to be immediately available as soon as I write that stuff. I don't want anything that's, when it's written, it will take a while for me to get that data. So you have the full flexibility to use the data in Kafka combined with your data in HDFS, put them together, you end up with exactly the same data source that we have in Elasticsearch. So all of this flexibility allow us to not really think about, well, no one can really predict what's going to happen in 2 years. The best thing is when you actually having a solution, you would better hope in 2 years, or it doesn't matter what time, when there's a requirements comes in, you have a structure that you can really, you're really flexible to deal with that problem. So why did we choose Elasticsearch? It's kind of coming to the Elasticsearch topic more specifically now. So a few things were mentioned earlier. I mentioned earlier in the earlier slides that some of these requirements from this report we wanted to achieve. So the first thing is, it actually did happen. So we wanted the new data field to be added to the system. And with Elasticsearch, although we do use strict schema, because we are dealing with transactions, we better make sure we know exactly what's going on. If there's an error, we better get told there was an error. We write all of that. So if we need to make a change, all we have to do is alter the schema to allow the new fields to come in. Let's say if we have other things like relational databases or whatever, you suddenly ended up with some, okay, do you have a new database? Or do you have to wait for the whole index to be rebuilt? So in our case, it's not only that. You add a new field, your data goes in, you suddenly get benefit from not just pinpoint queries, but also aggregations, and all the other things you can possibly have in that moment that you add that new field. This is something we're quite proud of. So I couldn't really run into exactly how much data we have because we're talking about transaction data here, but we have lots of data. And this, for the user experience after this was deployed, the average response time from our monitoring are mostly, well, are always less than 200 milliseconds. So every single response, that's including aggregations. So the user basically used to they moved away from, I had to wait for even 10, 20 seconds, even minutes for some of our big clients, to when they press the button for the last 10 years, they would get this in like 200 milliseconds. It's quite such an amazing thing for our clients to have. Well, I say adding nodes. Obviously, there's a lot of things you can do to increase the tune your cluster to really suit what you want to do. But let's say you got to a stage that really you couldn't really push this even more. You need more capacity, and all you have to do is to add more nodes into your cluster. And then obviously you have a cost of rebalancing as soon as you do that. So something to avoid at busy times. But as soon as the rebalancing is done, you would end up with cluster with much more capacity, which is something very easy to scale comparing to what it was before, and even some of the other storage engines. The REST API is really a good thing that we can use for a lot of the existing systems. So we don't want to change everything. Right? the existing systems, they're good enough serving the user request in the reporting APIs with authentication layers or presentation layer that give the user that user report. So with the REST API available to Elasticsearch, which made the transition process even easier. So we just implemented all of that stuff directly with the REST API in kind of adapter. So that allows us to really quickly deliver what we have in Elasticsearch to the clients. So now is kind of like a deep dive part about Elasticsearch. The reason I would like to go into these areas is because we do use it for transactions. So a lot of these things would be good to know exactly what happens. So if you have some data goes in, where is your data? Do you lose them? What is the durability? So these are good things we have to find out, we have to know in order to use it. So that's why the first thing I would like to talk about is transaction logs, refresh, and flush. So these are the three things that combine together to really, let's say, to ensure your data is there. But it's really understand at the beginning where your data came from, when you start indexing, at what point you would have the data available for search, at what point you have your data really persisted, that you wouldn't lose it when there's a node crashed in the cluster. So this is something I stole from the Elasticsearch documentation. I really like it, so I just wouldn't bother creating my own one. You can see it looks a lot better. So imagine you already have some searchable segments in the Elasticsearch with the commit points that you can query for the data. And now we start writing more documents into this cluster. Let's ignore the transaction log for the moment. I'll come back to that, and therefore I can explain why it's important. So it puts the data into a memory buffer, but the data is not searchable just yet. And the next step is it clears the in-memory buffer and puts the data in there. The reason it's gray is because it's not persisted yet. So that data you can search, but it's not on the disk. Later on, you add more documents, and it goes into the in-memory buffer again, and eventually the in-memory buffer gets cleared, and transaction logs gets cleared. So this is at the point I would like to talk about transaction log. So this last step is, if we don't think about transaction log, this is the only steps that your data is saved onto the disk. So imagine what will happen. So you have your node, you've been writing, so the flush doesn't happen that often. It only happens every so often. So that's not seconds. So imagine what happens is when you start writing, and then a few minutes later, suddenly the node actually got all of that data just died. All of that data will be gone. That's where the transaction log kicks in. Let's rewind a bit to the first one. So as your data comes in, the data is not only saved in your memory buffer, but also gets written to the transaction log, which is also called a write-ahead log. And after that, the memory buffer gets cleared, but not the transaction log. So that's already on the disk. It's not the data you can use it for this kind of search, but it's the data you could also, the transaction log is also used for pinpoint queries. If you know the document ID, that is, when your data is written to there, you can use it for get request and then delete request to actually get the data from the transaction log, not from here. But that's quite a limited functionality. And then more data comes in. Your transaction log gets bigger. Eventually, the transaction log gets cleared, and so I believe it does the flush first, and then it clears the transaction log. So and in this case, your data is properly indexed on the disk. So if this node dies now, not a problem. So you wouldn't lose your data. So now, with all of that, having said that, what is actually the durability of this transaction log? I know this is a very controversial topic, and there are lots of talks on the internet say Elasticsearch losing data, Elasticsearch not losing data, version 1, version 2, what's going on?
That's probably why. Is it still working? No? I think it's really just run out battery. Let me grab the other one. It's always the backup plan is good.
Thank you. Right, you can see the thing on the top right. That's the shovel. I'm digging a hole for myself now. So to talk about this topic. So I've done some research and even looked into the source code between the two versions. So we are still on 1.7. Something quite good to know is, if I understood correctly from all of these research I've done, is in 1.x, the fsync is by default set to 5 seconds. You can obviously set it to 1 second, but if you leave it as default, and it doesn't mean your data will be lost if that fsync hasn't happened. So this is talking about transaction logs. So it's not written to the transaction log instantly as you insert, as you index your data. So it takes 5 seconds, up to 5 seconds, for your data to be available on the disk. So if something happens in between, you would lose your data. So the funny thing is, I did actually try by killing the cluster multiple times, that very busy cluster. I just couldn't replicate it. So it's quite a kind of a thing, but that's one of the reasons why because we don't really know the answer to this at the beginning. So that's another reason why having a canonical data source in somewhere you really know that you're not going to lose anything is quite important. However, in version 2, this is quite a big difference now. So the default is now on request. So what that means is every time you have a index request, update request, or delete request, including bulk indexing request, your data is instantly flushed onto the disk at the end of that operation. So I haven't actually tried myself, so I don't know the difference in terms of performance. But the documentation suggests it's actually not much different. So it's something we want to try ourselves. And obviously it's probably a good idea for us to update to 2.0. We never actually had a data loss, but it would be good to have version 2.0 in place to really give us that guarantee. Obviously, you still have the option to set it to 5 seconds, so but it's not the default, I believe. I also would like to go through a bit of a refresh interval part in here. So obviously, a refresh is earlier what the thing that makes your data searchable. So you can start searching your data. The refresh interval is something that would allow you to define how quickly you want that data to be made searchable to the users. So I put 3 numbers in here because they all kind of used for different use cases. The first one, so what we use this for is when we have that disaster recovery process earlier in one of the slides. So that's pumping up like loads of data from the historical central DB into Elasticsearch. That process took like 5 to 6 hours. So obviously, if you set the refresh interval to -1, it will only make your data searchable at the very end. There's not really much point to make your data searchable in between because the data is not complete yet. So there's not really a reason to turn it on to, let's say, 1 second, just like doing it as you index your data. So it's not efficient. It's not really useful. So that actually made a huge difference. I can't remember exactly how much difference, but I remember at least twice as fast by setting that to -1. So 1 second, I believe, is the minimum you can set it to. So your data is not going to be available for search after at most 1 second after when you made the index request. So this is obviously very cool if you set everything to 1 second. But obviously it does come with a cost because I wouldn't go into too much details, but because every time you refresh, you get segments created, and later on this segment has to be merged. So the more often that happens, obviously the more expensive it is. So if you don't need that, so this is at the point I always go back and ask the business, all right, what do we actually need? So if the business doesn't need the data to be made searchable within 1 second, so why would you do it? You need a much bigger cluster to cope with that, much more disk IOs and all that stuff. So at this point, I always go back to the business and think about, okay, do we really need that? If we don't, so in our use case, the user is more than happy for 15 seconds to make the data available, which means we can have a relatively small cluster to deal with huge amount of requests, which saves a lot of cost in this case. So filters and queries this is one of the interesting things we found. And the reason I put version 1.7 in there is because version 2 had it's changed quite a bit. It's merged filters and queries to be one thing. But I believe some of these concepts still applies in this case. So which is the difference between the two and when to use one, not the other. It's actually one of the problems we solved that we couldn't find the answer anywhere. So we actually tried it and then figured it out. It actually made a huge difference by just using the other one. even for non-analyzed field. So obviously the difference between these two is the filter asks yes, no question. Is it there or not there? But the query asks a lot more. It say how well actually matched to your document. So you can see it's more expensive. But all right, let's consider these two examples. Can you read it from the back?
Yeah.
So I'll just quickly explain it. So on the left, it's basically these two are doing exactly the same thing in terms of the data you would get as a result. The one on the left is, this is the version 1 query, so the version 2, this is deprecated. So you have a tag, or many tags, and you turn the cache off. This on the left is using the filters. On the right is using the queries without a constant score. What that means is we'll try to calculate the score, but this is something I don't fully understand is why even you turn off the analyze field. So this field that we were running on it is not using analyze field. And it still takes, for this one on the left, took 76 milliseconds. This is the same cluster on a dev cluster, so which is pumping like a few million records in there. Live has so much more. So this one took 76 milliseconds, 3 million records. On the right, it took almost 20 times longer. So it's one of these things like one little mistake. Oh, one thing, let me rephrase. One thing I forgot to say. This is not 1, 2, 3, 4, 5 tags. We had the exact use cases of someone could have used 10,000 tags in this case. So it's not something people do all day. But in a month, someone did that, you better hope it works. So that's the actual use case we actually had in this case. On the live cluster, the difference was like 100 milliseconds and 5 minutes. Absolutely crazy. It increased substantially. So if you don't need that, turn it off. Don't use queries if you don't need it. So we are, as a company at the moment, we are not dealing with analyzed field. So all of the things I'm talking about are working with not analyzed field in this case. So just some suggestions I rewind here is some of the, if you could disable the analyzed field if it's not needed. So it's not only going to make the whole thing complicated with that tokenizer stuff, but also you could get the wrong data. So if you're searching for a string that has exactly that, but if it gets tokenized, you're not going to get it if you search for it. So if you don't need the analyze field, I wouldn't suggest just leaving it as default. Just turn it off with a flag to set it to be not analyzed. Also, obviously, use a filter if you don't need a query. Even I think in Elasticsearch 2, correct me if I'm wrong, I think 2 is still applicable. So if you don't need a query about scoring stuff, then use a filter instead. Doc value is the topic I like the most because it just gives you lots of free things, freebies for nothing. I try to summarize in a, I hope this is accurate. It's on disk data structure that allows you to do fast aggregations without the overhead of JVM heap. So what's happening by default is, let's say if you have some field with lots of data in there. If you need to aggregate by that field, by default what's going to happen is these data will need to be loaded into the JVM heap first, gets aggregated, and then give it to you. So there's quite a lot of overhead, as you can see, if you have loads of data. So we did some checks on our live cluster. So before and after, so without using doc values, we can see there's a spike on the heap and go to 100% pretty much, like all red in COF, which is one of the things we use to look at the Elasticsearch like health and other things in addition to HQ to see what's going on. And it's just every time. Especially the first time you're hitting, because after it's done the first time, it only has to do the difference. The first time is really expensive, and then the user gets really kind of substantial delays on the search queries. So after converting to use doc values, all of that heap no longer needed, because the data is now stored. I think version 2 is slightly different again, but version 1 is stored next to the inverted index as a data structure, so you can, when you need to do aggregations, it gets the data straight away from there and does your aggregation and give it to you directly without using the JVM heap. So as a result, you could set a much smaller heap size. So the typical suggestion is like if you have a 60 gigabyte node on a cluster, you set less than 32 gigabytes of heap on it. So you could do 31. Let's not go through why 32 is a problem. There's some kind of 32-bit pointer problems when you go over 32 and everything suddenly goes to the ground. I'm guessing you have to get to something like 60 and 70 gigabytes to actually bring that performance back. So set it to maximum at 31, not anything above that, I would say. So all of that RAM is, let's say if you reduce it from 32 to 4 to 16 gigabytes, and they're all available to be used by file system cache. File system cache, the more the better, right? Lucene works with file system cache really like a charm. So if you leave more file system cache, then your data is literally in RAM. The more of these you get, the better. So it's basically like all of these, the heap was previously wasted with these to just do the aggregations for the which are now can be replaced by doc values. This is now enabled, I believe, in version 2 by default. So if you're using version 2, if you're not specifically specifying you're using doc values, it is using doc values. Because the performance, even at 1.7, the version we're using, we can't really see much difference at all in terms of performance. Using the one with JVM heap and using doc values, we can't really see much different. So I would say even 1.7 is good enough. Obviously, we're not dealing with analyzed field. So if you have analyzed field, you can't use this for now. There might be more in the future further development to improve that. But at the moment, it doesn't work with the analyzed field. But hey, it doesn't stop you from using both, right? So if you have some of the fields that requires just direct filtering, but some of the other ones you need on heap aggregation. So that's still save you a lot of cost in terms of RAM. Oh, this topic again. It's one of the things like caught us out at early stages. I'm glad it was at early stages. Is some of the aggregations are approximate. So it doesn't really give you exactly what you want for a good reason, but not probably the reason you want it to be. Consider this case. It's not very easy to read. So you have an aggregation with the field product, and you want to get, so size 5 means you want to get the top 5, let's say just top 5 products of the whole data. But what actually happens is, again, this is, you probably look familiar, is one of the documentation page I really love. So let's focus on product C. So Elasticsearch are broken into shards, obviously. So you have shard A that has the number 3 is product C that has 6, counted 6 times. So these are all sorted from top to bottom, so they are in the correct order. On shard B, you would get product C that counted 4 times, and at C, you have it 44 times. By specifying you want top 5, it doesn't actually give you the top 5 of the whole thing. It gives you the top 5 of each one. So what that means is you have 6 plus 44, which is 50. That's wrong. It's supposed to be 54. For a lot of analytical things, this is more than acceptable. But for all use cases, disaster. Because what happens is your transaction is now 5% off. The total number of amount added, it doesn't add up. So it's something we found at early stages. Why the number doesn't add up? So it's something we really have some help from the other teams that we figure out. Oh, this is what's really causing the problem. The solution is simple and not simple. So you can literally just set it to 0. You can set size to 0. That would mean it would just get everything from each shard and then take whatever you ask to present it to you. That's always accurate. But however, it comes with a cost. And the cost could be quite high. Depends on the cardinality of your field. So let's say if you have filters, and you filter by something, only has 4 variations of the values. So your cardinality is very, very low. But let's say if I want to aggregate by second, every second I want to aggregate, and I have 5 years of data, I have no idea what's going to happen. So just as something to consider. But in most of the time, the business, this is coming back to the business again. What do we really need? Do we need by second? If not, reduce the cardinality to minute. If we don't minute, reduce it to hours. So there's a lot of things you could do or consider before adding more nodes to make it do that. So it's something really important from our point of view. The last thing is this split brain problem is very important. It's a very little thing that you can even configure and change while your cluster is running. But however, if you don't do it, it can lead to some serious data loss. Depends on whether you're lucky or not. If you're not lucky, it could happen tomorrow. So consider we have 5 nodes. Looks horrible on that. You have to consider you have 5 nodes, and number 3 is as present is the master node. It forms a cluster, happily receiving data, no problem. Suddenly, you have a problem that there's a network problem that 1 and 2 can talk to each other. 3, 4, and 5 can also talk to each other, but these 2 cannot talk to each other. By default, the number of eligible master nodes is set to 1. Obviously, by default, it wouldn't know how many nodes you would have in a cluster. If it sets to 3 and you only have 2 clusters, it won't work. So, but what that means is these 3 will elect their own master, happily receiving data. On the other side, it will elect their own master, happily receiving data. On the client side, you probably wouldn't even know if you have retries in place. So happily receiving data and all of the users getting their data, still correct for the time being. Now, your network is fixed. And the whole thing comes back into one cluster. Imagine this number 3 is still the elected master. And number 3 has no knowledge of what's going on with 1 and 2 because they couldn't talk to each other. What it's going to assume is all of these data, whatever 1 and 2 have, is out of date. So I'm going to delete all of them. So this is a typical split brain problem that you wouldn't want to encounter on a live cluster. You find out later on, oh, where's my data? Especially if you don't have a disaster recovery process like we have. If you only data, let's say even your data, you don't need 100% in there. But you still don't want to lose, let's say you found out 3 days later, you lost 20% of your cluster. That's probably not a good idea. So that's the end of my talk. You probably wonder what the hell that is. That's my Twitter profile. If you scan it with your phone or something, then we can talk about it. These are the links of, I can't really see it, but I believe the slides will be uploaded somewhere. I'll also put it on my Twitter link so you can find them later on. I really recommend reading some of the topics such as the deep dive of the doc values, exactly how that works. And if you really want to make sure you understand how reliable, how durable your data is, there's really good links about how transaction log works. So I think that's the end of my talk. Welcome for questions.
Yeah, so we're going to plan B. We've only got 1 microphone, so I'm going to sprint round to anyone that's got any questions. Oh, we've got a taker.
Thank you, great talk.
Thank you.
Quick question. So you're indexing into Elasticsearch from Kafka using Spark Streaming.
Yes.
What are you doing in Spark Streaming? Anything clever, like aggregations, or is it just A to B?
No, it's just A to B. There are some.
It's simply just it's kind of like a real-time ETL job. It's simply just taking the data from Kafka in near real time and put it into Elasticsearch. There are, however, some mapping going on, some business logic going on, but not a lot. So that's the main thing, that we basically just take the data from there to there. Because in our use case, Elasticsearch does most of the hard work for us. So the main problem for us is real-time aggregation that we couldn't do before. And in this particular case, it solves the exact problem. This other thing is we're not doing aggregation in Spark Streaming is because it's very actually difficult. So what you probably realized is we're not implementing a Lambda architecture here. This is more towards the Kappa architecture, so you only have a real-time layer. The disaster recovery process is not really part of the picture. It's just something to help us if something goes wrong. So we are dealing with mutable data here. So if in our use case, something that happened, something is being created, let's say a transaction created 7 months ago, could get changed yesterday. So it's much easier. I don't really know at the moment another way to deal with this problem by using Lambda architectures, because you don't know where the data gets updated. You can aggregate or pre-aggregate the whole thing, but the next second your data could be wrong. So it's much easier to have all of the data written into a data store as individual transaction records than gets aggregated with Elasticsearch, which fits our use case really well. Does that answer your question? Thank you.
Anyone with any other questions? I think there's... Yeah, I've got you.
Hi. What happens in the disaster recovery process after the split brain? So what have you guys implemented?
Sorry?
What have you implemented for the disaster recovery in case of split brain?
So split brain would not happen if you set your cluster's minimum eligible master node to, oh, sorry, this is my bad. I forgot to explain there's a fix. So you, let's say you have 5 nodes in this case. The number of eligible master node you have to set to make sure this problem doesn't happen is 5 divided by 2 plus 1, which is 3. So I'll go back a little bit. So in this particular case, so the split brain would only happen if your eligible master node is less than the required. And what's going to happen if you don't have the minimum number of master eligible nodes, they will elect their own cluster. They'll elect their own master and then start forming one. But in this case, let's say if you do have 3 eligible master nodes and all of these 5 nodes are master eligible, what's going to happen is these 3 at the right will happily form their cluster. The one on the left, they can't be used because they can't elect a master because there's no 3 nodes that are eligible to have a master. So the formula is basically number of nodes divided by 2 plus 1 to solve that problem.
Any other questions? Yeah.
Sorry, it wasn't a question, it was more just a comment. Thanks for the talk. Master nodes, we would always say the answer is 3. And 2, obviously being the quorum. Anything else is an architectural compromise. Let me run through the logic. Master nodes shouldn't do anything other than be a master node. They shouldn't do any indexing, they shouldn't do any searching. If you make them double up in activity and do indexing and searching, then they're subject to the possibility of kill a query, kill a document, and you then put your cluster at peril. So that's why we would say use dedicated master nodes. If you only have 1 master node, then that's a single point of failure. So you would need a backup. If you had 2 master nodes, master eligible nodes, you have the possibility of a split brain. So that's why you have a third as an arbitrator. So between them, these 3 nodes sit around doing not very much. One of them is elected. And if it has a bad time, the other 2 decide between themselves who's going to take over. So the answer, for my money, is always 3 dedicated master eligible nodes. But not many people actually want to spend money having machines sat there doing nothing. So there's always kind of a compromise that or there's often a compromise. But for a proper system, I think anything else is a compromise.
Thank you.
So dedicated master nodes, they don't do much. As I say, 2 of them are sat idle, just waiting to make a decision between themselves when the other one dies. And the one that is performing a function as a master node doesn't do an awful lot of work other than keep its eyes on the other nodes in the cluster and update mappings and that kind of thing. So it's not actually involved in. It's more of a managerial function than a worker bee, if you like. So it's not indexing, it's not searching, it's just sat there kind of looking after your cluster. And just one other little thing on the size thing and the accuracy. There's a thing called shard size, which is pretty key. So size is how many things you want back as a final result. And shard size is some kind of multiple of that you ask each node for. So if you ask for the top 1 of something, each shard doesn't get asked to contribute 1 result. It's actually some kind of multiple of the number of shards. They might each produce their top 10, which then gets merged together. But you can pick a larger number for shard underscore size.
Right.
And that helps you kind of tweak the accuracy a little bit. Oh, sorry, yeah, my name's Mark, and I work for Elastic, so yeah.
Thank you.
Just in case you guys were wondering, there's going to be a Q&A at the end with these two guys from Elastic. So I just thought, yeah, might as well just introduce them while we're speaking at the moment. Any more questions? Yeah.
Is your system in-house or is it hosted?
It's in-house.
The question is our system in-house or hosted? We have in-house. We have the live IT team maintaining the cluster.
Okay, we've got space for one more question. Relays.
Just a question, you're on version 1.7 at the moment. Have you put much thought into the upgrade path? And
Yeah, that's exactly
So-
what we want to do.
The question is, have we put much thoughts in 1.7, and are we thinking about upgrading to version 2? 5? Is it called 5 now? Oh, right, that's the new one, yeah. Yeah, so, yeah, obviously for good reasons, if my observation or research was correct, that version 2, in terms of the transaction logs, gives much more guarantee. So this is something we're certainly looking forward to upgrade to a much newer version. Yeah, I think we started falling a little bit behind now because we start seeing things get deprecated. So that's good. It's usually a good sign to upgrade to another one. So because again we have all of this architecture built for entire rebuild from scratch, so we can easily upgrade. It's not gonna be a difficult job.
So thank you very much, Richard.